Okay, so we are very happy to have Ki-Seok Kim today from POSTECH. So Ki-Seok graduated from Pohang University in 2004, and then he did a postdoc at the Korea Institute for Advanced Study, followed by postdoc at Saclay in France. And then he obtained a research professor position at the Asian Pacific Center for Theoretical Physics. In 2012, he joined a postdoc in Pohang as a faculty. So Ki-Seok's work has been mainly focused on transport and phases of strongly correlated systems, as well as topological properties of matter, particularly regarding biseeming methods. And lately, he has been working on emergent gravity and holography. So today, Ki-Seok will talk about emergent holographic dual effective field theory as a mean field theory in the large and limit. Please, Ki-Seok, take a lead.
Thank you. First of all, I would like to thank Shinsei for giving me this nice opportunity. And I also appreciate the preparation of Paolo for this video seminar. So here, I will talk about emergent holographic dual effective field theory. In particular, an important point is this effective mean field theory takes into account all loop ordered quantum corrections in the large and limit. So the slogan of this talk is RG equal geometry. This is my slogan. So this presentation is based on my recent work with Shinsei. So holographic duality conjecture states that for the space-time dimensional quantum field theory, there exists one higher dimensional quantum gravity theory. So, but if I try to translate this statement into condensed metaphysics language, I would like to call this: there is an effective Landau-Ginzburg field theory which lives in one-dimensional higher space-time, where the coupling constants are given by some emergent metric tensor, are renormalized. This is the statement. So usually the extra-dimensional space, the distance in the extra-dimensional space is interpreted as an RG scale. In this respect, one may think that the holographic dual effective field theory manifests renormalization group flow of the effective action through the extra-dimensional space. So it describes strongly coupled physics in terms of dual fields, particularly metric tensor and order parameter and gauge fields. So their coupled equational motion in the large and limit describes such strongly coupled physics. So in addition, there can exist some phase transition in the geometry. At low temperature, ADS geometry can turn into ADS black hole at high temperature. As a result, one may have some effective hydrodynamics at high temperatures. Here, I would like to derive this holographic dual effective field theory. So let me recall the effective field theory for weakly correlated electrons. So basically, as all of you know, it's given by PCS framework or Landau-Ginzburg theory. For strongly correlated electrons, I will implement renormalization group transformation. So this Landau-Ginzburg effective theory contains renormalized coupling constants, where such renormalized coupling constants manifest through their RG flow through the emergent extra-dimensional space. In other words, this Landau-Ginzburg theory manifests their RG flow through the natural introduction of the extra-dimensional space. This is the basic philosophical statement. So I will implement functional renormalization group transformations in a recursive way. As a result, I construct or I derive some effective action which manifests algebra flow through the emergent extra-dimensional space. So C1, C2, this X is basically some coupling constant. Usually performing the renormalization group transformations, you have some algebra flow of this effective action, but in the effective action level, the algebra flow does not manifest in itself. But here, we will manifest such an algebra flow. So this is the end of the part of the philosophical statement. So if you have any comments or questions, yeah, please. If not, yeah, let me proceed. Now, let me summarize the main result. So I'm considering the ON vector model. So this is the ON vector field. Alpha runs from 1 to n. This is the UV effective action. So phi alpha is the ON vector field. So I put this scalar field theory in terms of background metric, in the background metric. So this is the mass term. This is the curvature induced mass term. This is their self-interaction term with coupling constant U. So this is the energy momentum tensor interactions. Although this is irrelevant, at first let me keep this one. So what I performed is that in terms of dual field, phi is dual of this density. G mu nu is the dual field of this energy momentum tensor. So I derive this bulk effective action with the extra dimensional space coordinatized by Z. And they are supported by UV and IR boundary action. So more.
Sorry, can you go back?
Yeah.
I want to understand better the UV action. So T mu nu alpha is what?
So this is the summation alpha is omitted. So T mu nu is the energy momentum tensor of this effective action. So derivative with respect to Gb mu nu, you have some
What's
energy.
The alpha index?
Alpha is summation of alpha.
I don't understand what T mu nu alpha is. A stress tensor has 2 indices. Why is there a 3rd index?
Sorry, alpha is the flavor index, the ON vector. So alpha runs 1 to n, mu nu is space-time index. So basically, mu nu space-time, you may neglect this. So this is order of n, I just divide. So summation alpha is sum 1 to n, that's it. So sorry, yeah, we don't need.
So T mu nu does not have an alpha index. It's just the ordinary energy.
Yeah, sorry, yeah, just sum of alpha, yeah.
And in the quartic term that you have written there, what's going on with alpha and beta in that expression?
So this is alpha 1 square plus alpha n. So summation of alpha and summation of beta. This is, yeah. So all summation of alpha and summation of beta is omitted. Yeah. Sorry.
So that's an ON invariant quartic.
Yeah, ON invariant. This is ON invariant quantity. So all is ON invariant.
What's going on with the curvature interaction? Why do you have a RB curvature interaction with a arbitrary coefficient there?
So basically, I start from Euclidean space. Basically, I do not have this term here, but just in case, if I set this in general curved space-time background, I just set here, yeah. But here, I start from Euclidean space. It does not have. So basically, metric tensor is given by delta mu nu. I just formally write here, yeah.
Okay, but by what principle are you fixing the coefficient in front of that quadratic term?
here.
Or do you leave that to be an arbitrary coupling constant? Or what exactly?
Basically, I set it arbitrary coupling constant. So I don't have any idea how to fix this coupling constant here. So it's basically arbitrary coupling constant here.
But is the sign positive or negative?
So Ki is, as far as I know, set to be positive. Am I correct? Yeah. So this is, but here we start from Euclidean space. We have some, vanishing curvature here. I just rewrite this OM vector model with the introduction of some formally introduce some metric tensor. That's it. Yeah. That's it.
Okay, so you want to leave that coupling.
Yeah.
Okay, so what is and then you said that var phi is a dual field to phi
Of the ON invariant density, phi alpha square. Yes.
You mean var phi is equal to phi alpha squared? What is var phi? What is the expression?
So
for
in the mean, var phi is Hubbard structural field of phi alpha square.
Okay.
In the mean field level, it's vacuum expectation value, but you don't. This is just dual to this phi alpha square. Yeah. Yeah, you will see soon. Yeah.
Okay.
So yeah.
All right. Thank you.
So let me give some just result overview. I will show the detailed derivation.
Sorry, excuse me. Can I ask?
Yeah.
So you have the T mu term, but how you define the T mu, or if you define the energy momentum tensor by taking the variation with respect to metric, it seems it contains T mu. So I don't know. Yeah.
So right. So basically, forget set to be I set lambda equal 0.
Mm-hmm.
Then you can have variation, this effective action with respect, variation with respect to G mu. Then you have T mu.
Mm-hmm.
Then I introduce this effective tensor interaction. That's it.
But is it what is the main motivation to introduce such a very?
So the main motivation, although will be clarified, but this irrelevant interaction for weak lambda, it promotes the metric tensor be fully dynamical. You will see. So at first I will set lambda equal 0. I will not consider this one, but later I will consider this one.
Mm-hmm.
But this lambda, you will see in the next slide. So,
but I guess maybe if I could ask the same question.
Yeah.
The stress tensor is the variation with respect to the metric, yeah?
Yes, right.
So I don't see the dependence on alpha there.
Yes, you are right.
Metric is independent.
Yes, you are right. Alpha sum, this must be summed. So internal index should be summed. Sorry. Yeah. Yeah.
Okay.
Sorry. Sorry. So the main result is the bulk effective action is given by this one. So var is the dual scalar field, dual to this one, which results from Hubbard-Strauss transformation of this one. At x equals 0, it's certainly dual to phi alpha. Summation alpha is omitted here. As a standard some kinetic energy term, you have the G derivative term. So this gives rise to flow along the extra dimensional space. In addition, so lambda is the coupling constant between energy momentum tensor effective interaction. So this term describes the evolution of the metric tensor. Here, G derivative here. So general structure is given by metric tensor evolution is given by so the green function of the high energy propagator of the previous bosoning matter. So this is the typical expression. This is so dz is the RG scale, which will be clarified. So G is the green function of a high energy fluctuation of the bosoning field, the original boson field phi alpha. Then these high energy quantum fluctuations of these bosons generate effective geometry, their RG flow. So their irrelevant effective interaction gives rise to this square behavior. So, and also Einstein-Hilbert action in the X, in the d-dimensional space-time. So this is the general structure. So this is the bulk effective action. You will see how I obtain this one.
Sorry, is the metric now a dynamical variable?
Yes, the metric is promoted to be fully dynamical. Yes, right.
And, I'm a bit confused about just making sure I understand. D is the dimension of the boundary?
This is the space-time dimension.
Okay.
Space-time dimension, yes.
And G is
extra-dimensional space-time, extra-dimensional space. Dually emerge, it is identified with the renormalization group scale. You will see explicitly, yes.
okay.
Yeah. So so this is dual field of ON invariant density and energy momentum. This is the result of renormalization group transformation, and IR effective action is given by. So this is all a coefficient. You will see how I obtained this one, but so this is the boundary action, IR boundary action. GF is the IR boundary. So the same, but except for there is no G dependency here. Of course, the true IR boundary condition is given by the boundary term of this bulk action. This is the UV boundary action. So this I would like to call this effective Landau-Ginzburg theory in the large N limit, where this is the order parameter basically at x equals 0. This order, so as you can see in this expression, G, the green function contains metric tensor and order parameter. This evolution term is highly nonlinear and non-linearly intertwined with the renormalization group flow of the order parameter and metric tensor. They have some very intertwined structure. So variation with respect to this order parameter metric tensor, you will have coupled equations. That's the basically description for this one.
Sorry,
Could you point? Okay.
sorry, could I just ask, what's setting the cosmological constant, lambda?
So lambda is basically vacuum energy, which result from high energy quantum fluctuations in the renormalization group transformation. You will see.
Why does it have a definite sign, or the sign could be either sign?
Although I did not carefully check out, so at present, I don't know at present, but I can have formal expression here for this one, but I didn't check out. Yeah, the sign. Sorry. Yeah, I understand.
Thank you.
But is this bulk action weakly coupled? What is the size?
So in the large N limit, I will take the large N limit. So in this case, yeah, I will neglect quantum fluctuations basically. So this is in the large N limit weakly coupled. Yes, right.
So the claim is that the curvature and lambda are independent of N. So that's the only N scaling is the thing that you've written?
Yeah, here, yes, yeah. This is just a vector model where the vector index is given by the flavor index 1 to N, alpha 1 to N, yes. All are independent of N here. This is only N dependence, yeah.
I have a question on the reference to Ginzburg-Landau. Is there a symmetry breaking at this point?
It depends on the solution. So if you see the green function here, you can have some condensation of this value. Then the mass of this bosonic degree freedom of original field can have condensation. You will see, yeah. So basically, the effective mass can be negative, which depends on the value of this value. Yeah, this dual field. Yeah, it can give some symmetry breaking. Yes, right.
But can
Yeah.
you read off the vacuum manifold already from this stage, or that you have to do more work to find that?
Pardon?
So the vacuum manifold, I mean, the generic picture I had in my mind for Ginzburg-Landau symmetry breaking.
Yes.
The vacuum manifold is a algebraic, essentially, manifold that you can identify from the functional.
Yes, you're right. But here, I consider the only ON invariant object. So if you really want to deal with symmetry breaking properly, you should introduce some vector potential as an external proof. I will come to that kind of thing. Yeah. So here, symmetry breaking is not completely well treated. So symmetry is not. So here I consider only. So basically G2. Yeah. Phi is. So here I consider only the density field as just startup. Yeah. So symmetry, you will see. I will discuss to introduce the ON gauge field as a background gauge field that can describe some symmetry breaking properly. Here,
Question. How do you define the SIR, the IR action? Is it like after integrating out of bulk fields, or it comes from boundary value, well-defined of the boundary value problem?
So although you will see this one, but basically if you integrate out, I think you will see soon. So basically what I mean is integrate out original Boson field, then expand this order parameter field, then you will have this action. But you will see explicitly soon. Yeah. So it will be clarified soon. So yeah, right. So let me skip this one. So basically what I want to say is physical ingredient of the metric tensor and order parameter field IR boundary condition. I will discuss this part, but this is so what I want to use is just renormalization group transformation with the background fields in the almost tree level. That's it. It's very simple. You will see. So let me derive. So first, I perform the Hubbard structural with transformation for the self-interaction. So for the time being, I neglect the effective tensor type interaction. So I'm considering only self-interactions. Then phi 0 is the dual field of phi alpha square density. Then to prepare renormalization group transformation, I introduce an auxiliary field which does not change the partition function, just except for the normalization constant. Just integrate out this eta field, you have just the overall constant. That's it. Now, from this one, I separate slow degree of freedom and fast degree of freedom. Phi 0 is slow degree of freedom, Chi 0 is fast degree of freedom. These two coefficients are determined by the fact that the cross term in this mass term are to vanish. So that is given by in this way. So others are not important. The important point is this is the high mass term. So just plugging here and just calculating, then I have some mass term is given by this one and this one. This shows why I call this slow degree of freedom, this fast degree of freedom. So beta 0 is the local speed of coarse graining, and dz is the renormalization group scale. So beta 0, later I will relate this local speed of coarse graining with some lapse function in the ADM formulation in the Hamiltonian gravity. Then as you can see, this is very small value dz. So this is 1 over dz. Basically this is dz. So very high mass.
So I'm just a bit confused about the
yes.
Is dz small?
Yeah, dz is very small. Yes, right.
I see.
Yeah, so basically this was introduced by Polchinski and further developed by Sung-Sik Lee. So this is the completely same technique. So this is the original term with this one, and this is a high mass term. So that's the reason I call this slow digger freedom, fast digger freedom. Then I rescale, which returns this original mass term into the original expression. Then I integrate out this heavy mass term, heavy Gaussian integral. Then complete the same thing. So new effective interactions are generated. So as it must be, yeah. So then an idea is I perform Hubbard-Strutowitz transformation again and update this variable in terms of this new order parameter field phi1. So I already shift here. So now original term phi0 I shift here. This is promoted into phi1. This is the technique that I use. For the renormalization group transformation for the matter field, I also introduce an auxiliary field which does not change the partition function except for the normalization constant. Then again, I divide the slow digger freedom and fast digger freedom. And these two coefficients also determined by the fact that their cross term doesn't appear. Then mu0 is the mass term, the high mass. Just plug in these two coefficients, then I obtain this term with the original mass term and high mass term. High mass term is given by 1 over dz. So this is so that's the reason why I call this low energy fluctuation, high energy fluctuation. Then I again rescale this term, which returns this term into the original expression. Then I obtain this effective action. So as you can see, this is the original mass term, high energy quantum fluctuation term with the high mass here. This is the coupling term. Then it is straightforward to perform the Gaussian integral for this high energy quantum fluctuation term. Then I obtain this one. So I keep all the terms up to the linear order in dz, and the Gaussian integral for this high energy quantum fluctuation term gives rise to modification of the kinetic energy term in a non-local form. G is the Green function of a high energy fluctuation bosonic field. Here it's given by 1 over dz. So this is the high energy quantum fluctuation Green function. Then integrating out high energy fluctuation term, then I have this log trace log something. Then I expand.
I have a question.
Yes.
Why did you call this renormalized Green's function term non-local?
Sorry. So non-local means that this term will renormalize the kinetic energy term here. But as you can see, this is x prime. So this is non-local.
See. Yeah, thank
you. Yeah. Sorry. Yeah. This is non-local term. So yeah, that's the reason. So this would
convolution. Yeah.
Yeah, exactly. So all technique is just Gaussian. That's it. Yeah. And also, I expanded this one, G mu nu and phi. I perform gradient expansion with respect to m. Then I obtain this Einstein-Hilbert action. So sorry, this C lambda CR I didn't check out carefully, but this appears from these high energy quantum fluctuations in a standard way. Then also I expanded this one. I obtained this gradient term. typical kinetic energy term. But this all coefficient has to be calculated from the gradient expansion of this action, but I didn't carefully check out. So the sign of this one, I'm not sure. Yeah. So this is called the induced gravity action from here. Yeah. So the main approximation is that I neglect the non-local propagator. So basically, if you recall here, in the DG zero limit, the mass is very high. So in this respect, you can consider the expansion with respect. So I keep only local term. You can consider gradient expansion, but the DG also appears in the same way. So in the DG zero limit, the leading order is given by this one. So I keep only the local term here. Of course, the reasoning is very simple because now so this renormalized term is combined as in this way, in a simple form. That's the reason. So finally, you can update the metric tensor. All the same as follows. So G1 is now from G0, you have this term. So this is the green function of the heavy propagator. So yeah, this is the typical structure. So the technique is very simple. In the presence of background field, I integrate out high energy degree of freedom in the Gaussian level, although I expanded some log term here in this way. So physics in this calculation is as follows. I'm considering large N limit. Then, as you can see, large N limit here. Then you can integrate out phi alpha here. Then you also the same thing. Then in the large N limit, I have some effective coupled equations with all these three fields. And the ingredient is that for phi 0, this is the conventional mean field theory equation. In addition, I performed the renormalization group transformation, where I performed the path integral for fast mode in the meta sector that gives rise to some renormalized coupling constant described by updated metric tensor. And also, I performed the path integral for fast collective excitations in the order parameter sector that gives rise to 1/n correction. That's usual. Then also, this is fully self-consistent. So this calculation describes self-consistent mean field theory with the one-loop quantum corrections in the large N limit. This is what I have done in this calculation. And the order of path integral is not important as long as epsilon goes to 0. This is the small parameter which controls all the calculations. Previously, I showed the alpha 0 and beta 0, the local speed of pulse graining, and TG is the renormalization group transformation scale. So this is the d-dimensional space-time described by background metric tensor here. Then I perform renormalization group transformation. Then I have dg, so g equals 0 here. Then also update the metric here. So this local speed of pulse grading corresponds to the lapse function here. So the reference frame can be different here and here. So GDD is set to be 1, and their off-diagonal term set to vanish. That's the gauge condition here that I used. So without thinking, simple calculation, I fixed the gauge, GDD 1, and off-diagonal vanishes. This is the background metric. And 1 is determined by the RG flow of the metric tensor given by the propagator of high energy quantum fluctuations. The final step is to repeat this renormalization group transformation. Now I perform renormalization group transformation, Phi1, Phi1 and Phi alpha. Phi alpha is matter field, I repeat, and cut is below smaller. Then the bulk effective action is given by, originally I have 1, 0, but I repeat this. Then here dz and dz here. The minus sign comes from I observe the imaginary I into this field. Also, the evolution of metric tensor is given by in the same way, same form. This is also same form. And the green function is given by this one. I just repeat. So first iteration already ends the recursive expression. So this is UV action. This is IR, boundary action. Fully renormalized metric tensor appears in this IR boundary action. So the physics also the same. So in the large n limit, I have the coupled equation. So this phi 0, phi f, and G min 1, G min f in the large n limit. This is the mean field theory, and also I perform the recursive algebra transformation. I would like call this vertex that gives rise to vertex correction for described by this coupling constant given by metric tensor, and this order collective variable fields integration generates 1 over n, 1 of blah blah 1 over nf quantum corrections. F is the iteration number of renormalization group transformation, and plus self-consistency. So I use like, indeed, you can check order by order this integral for this collective excitation give rise to 1 over n, 1 over square quantum corrections in the presence of background fields, as it must be. So I would like call this self-consistent mean field theory with some non-perturbative quantum corrections in the large n limit. So infinite order loops are resummed. I'm not saying this is exact. This is far from exact because I will not perform the final path integral in the large n limit, but infinite order loops are resummed. So also order of the path integral is not important in the epsilon 0 limit, dz 0 limit. So the final step is to make this discontinuous some iteration step in terms of continuous variable. So this is translated into G integral. Now K is promoted into some continuous variable G. Now I replace this expression in terms of metric extra dimensional coordinate Z. Then you can rewrite the previous expression as follows. Now the expression is much prettier and simplified. So this is the emergent extra dimension, and this is d-dimensional space-time. This is the order parameter dynamics. So minus sign, I already mentioned, I is observed. Then the same, and Einstein-Hilbert action. And this metric is evolving through this.
I have a question.
Yes, please.
When you go from this discrete sum above to this continuum, you're identifying ZF there. What determines ZF a priori?
GF is basically IR cutoff. Here I'm basically GF goes to infinite in principle, but basically I think it can be IR cutoff 1 over temperature. If you consider finite temperature, it can be 1 over T. Yeah. So let me say in this way. So original UV effective theory is defined as some cutoff scale lambda. So now I integrate out, so decreasing the cutoff lambda. So in this respect, GF is identified with the UV cutoff scale in the original field theory. So lambda goes to infinite and GF goes to infinite. so all regions are integrated out. That's what I'm thinking, yeah. So this is the renormalization group scale. So here I used some real space algebra, but you can consider in the momentum space. So original cutoff, you can, so it doesn't matter. You can implement this algebra in the momentum space or real space. In momentum space, you integrate out the momentum region. So from lambda to lambda minus t lambda, and again from to lambda minus t lambda to lambda minus 2d lambda, and so the cut is lower. So in this respect, I think this GF is identified with the original UV cutoff. So this integral means that the full integration is performed during the renormalization group transformation. Yeah. So 2DGF is the full integration region of the system. Yeah. So this is the UV boundary action and IR boundary action where fully renormalized coupling constant appears in this way. So this is the effective action. So this is the Green function of a high energy fluctuation propagator. That's it. So as I mentioned to you before, this Green function is a functional of a metric and order parameter. So here their evolution is highly non. Yeah. So although this almost tree-level calculation has been performed, the resulting classical field theory contains complicated nonlinear renormalization structure. So this is shown in the archive. Suppose I introduce some, T-mu tensor, then in the same way, I perform the Hubbard-Strauss transformation for this one. Then I have some dynamical, some metric tensor. Then I introduce some auxiliary field and separating slow and fast degree of freedom. And I perform the fast integral for the fast degree of freedom, which achieve some renormalization group transformation for the metric tensor. Then I will obtain this square term. Here the main point is that as I performed for this order parameter field, I consider only Gaussian integral. Here, as you know, metric tensor contains dynamic sum metric tensor contains highly nonlinear term, but I neglect all the nonlinear term. I keep only the linear Gaussian fluctuation term. Then I have this kind of effective action. So the main point is this square term given by, so this is basically some, sorry, I didn't cite this. So CAD is TT-body formation. So I have this one. So now the order parameter field and metric tensor are promoted to be fully dynamical. So again, this high energy propagator of the Bojonic method, original Bojonic method, also contains metric tensor, this one. So this is nonlinear equations. So beyond the usual Einstein gravity. So this is Einstein Hilbert action, but their renormalization group flow turns out to be much complicated. This is the Gaussian order calculation, but in the DG goes to zero limit. That's it. So gauge fixing is given by 1 and 0. That's it. So this is the full holographic theory. So I integrate out this matter field, then I have this one, then I perform gradient expansion for this one. Then I have this effective action. Now the effective field theory is given by in terms of dual field phi and p mu, dual to energy momentum tensor and density. So this is the bulk effective action. So this square term is given by their effective interaction. Their renormalization group flow is given by this term and this term. Now in the large N limit, you have some coupled equation of motion for metric tensor and dual scalar fields. And I will show some Einstein, some metric evolution equation correspond to RG flow of the coupling functions. Dual scalar field equation is the order parameter equation, and IR boundary condition describes mean field equation with fully normalized coupling functions. That's the physics. So in this prescription, I'm saying this is the RG improved self-consistent mean field theory, where some quantum corrections are resound. So this is the large N limit theory. So this is the end of the technical derivation, although as you can see, it's very straightforward. Although technically, because I should deal with background metrics, so maybe some technical difficulties, but except for that, the renormalization group transformations are completely straightforward. So this is the end of the technical part. Any questions?
I have a technical, it's more of a language question. So you've been using the word dual in relation to the metric tensor, referring to its dual being the stress tensor, and the
yes.
field phi is dual being the density.
Yes,
but in the first sentence, large N limit, you refer to it as a dual scalar field. What's the meaning of dual there?
Dual. What I mean is dual scalar field. This one.
Yeah. So what is the meaning of dual there? So you've got dualities between the metric and the stress tensor.
So
density. That's a duality. I'm just
yes, right. Yeah, phi is the dual field of the density phi alpha square.
Yeah.
That's it. Yeah.
I'm asking the question in the first sentence in this slide. You have the sentence which begins large N limit in black. You use the word dual there. You refer to it as a dual.
This one.
What is the role of the word dual?
So I have two kinds of scalar field. One is original matter field phi alpha. This is far phi. So I'm saying far phi. That's it. Sorry. So collective scale. Yeah. So order parameter field. Yeah. What I'm saying metric tensor and order parameter field far phi. Yeah. Sorry. Just I read. Yeah. That's it. So to figure out, yes, please.
Could I just check one or two things? So the ON model here is special only because you can take a large N limit and neglect a bunch of interactions, or suppose I replaced it with something else. What stops me from doing the same procedure?
So you mean replace bosonic theory to fermions? Or
yeah, just replace ON with your favorite quantum field theory. Perform RG flow with a Born-Oppenheimer approximation, and then try and rewrite it in terms of interpretation, in terms of a dynamic metric.
Yeah. So although I didn't explain this part, but that is related with the previous first question. Here, ON symmetry is not treated properly. So even for the ON vector model, if you consider ON symmetry, you should introduce ON background gauge field. Then the gauge field, also you can introduce such a ON invariant some interactions. Then the theory becomes much more complicated. But suppose if I consider some fermion Dirac theory with interactions for dynamical mass Psi interaction, also current interaction. Suppose I have Dirac theory with the mass operator interaction and current interaction. Then if you perform the same task, basically you have essentially the same structure, but this order parameter is dual to the mass operator Psi, and also this G mu is replaced with the Fierbein. This double derivative is replaced with the Dirac operator, and this green function is replaced with the Dirac propagator of high energy Dirac spinor fields. So this structure is robust because if you recall how I perform renormalization, Born approximation or tree level or Gaussian integral, that is basically gives us this kind of structure. So yeah, that's it. So for the current interaction, you also have some dynamical U1 gauge field. So yeah, there exists some additional term. Depending on the some effective interaction, symmetric current, you should introduce some background field to measure, to couple such conserved current. Yeah. Then you repeat the algebraic transformation, and then you obtain this bulk effective actions. That's it. This is quite general structure in this level. So to show the physical meaning of this emergent holographic dual description, let me consider some different renormalization group scheme. So what's the meaning of metric tensor evolution? So now I'm considering 1+1 dimensional lattice field theory, lattice scalar theory. So this is a hopping term, I plus 1 site, time fluctuation term, mass term, self interaction. Then I implement Kadanoff block spin transformation, which means that I separate the even and odd site. I integrate out all dynamical fields at even site. As a result, I obtain an effective theory for odd site versions with renormalized coupling functions. Also, some effective interactions are newly generated. And again, I perform some Hubbard structure, I repeat again. Then, so this is the original Boson field. So Phi is the Hubbard structural field of this density. Then this is fully renormalized coupling. Then the mass parameter and hopping integral and self interactions are renormalized in this way. The detailed expression is not important. It's straightforward. I just repeat even and other site separation, integrating out even site. It can generate some new effective interaction for other site versions and Hubbard structural transformation again, and I repeat the same procedure. And this is the bulk action. So quite similar structure with this one. Now the effective action is 1+1+1 or 3-dimensional. So this is bulk action, renormalization group transformation, renormalization group beta functions, and IR action and UV action. The same structure. So what I want to compare is, this is the previous effective action in the lattice model. This is the effective action that I showed, but here I neglect the tensor type effective interaction, and also I assumed translationally invariant solution as a vacuum solution. So I neglect X dependence here and here. What I want to say is this partition function is essentially the same as this partition function, regardless of the I used different renormalization group transformation method. Then you can identify this first part into this one, and IR action with this IR action, bulk action with this bulk action. Then although you can say this is this time component and space component, although this 3 parameter, but actually due to this one, then here, and actually 2 parameter. So here two independent parameter, phi here. So gt, gx, and phi tilde. So then you can make some comparison. As a result, you can rewrite the evolution equation of the metric tensor in terms of the running mass parameter in the lattice model. So in this respect, the renormalization group flow of the metric tensor takes into account the RG flow of the coupling constant. This is what I'm claiming. The second is, let me consider some boundary conditions. Since the metric formulation and the lattice formulation essentially same, so let me consider the lattice formulation. So this is the typical free energy of non-interacting bosons. So log sine hyperbolic relativistic bosons. But here, these coupling constants are fully renormalized. And so this renormalized coupling constants are described by this RG equation. Performing variation, this bulk equation with respect to order parameter, you have some bulk equation. It's straightforward to solve this equation. Then you have this one. Detailed expression is not important, but UV boundary condition is given by this one. This is the UV term, and this linear in G derivative term appears from the UV boundary term of this bulk action. Then solving this one, you find the phi 0 equals 0. Then this is the solution. Finally, the IR boundary condition is that this is the IR free energy with the IR boundary term from the bulk action and variation with respect to phi, and you have equation of motion for IR boundary condition. As you can see, this looks similar to the mean field equation, standard mean field equation, but all the coupling constants are fully renormalized. In particular, inserting this renormalization group beta function for this one into this one, then you have this one. So this mean field equation is supported with the fully renormalized coupling constant. To check out in the GF equals 0 limit, this is one iteration limit. Then you have, this is now is a pair value, the original value. Now this is a one loop RG. So this is the mean field equation, with the one loop RG transformation. So one loop RG improved the mean field theory. This is the limit. So this is what I'm saying. The IR boundary condition contains the all loop order quantum corrections in the mean field equation where coupling constants are renormalized by the renormalization equation. So finally, let me consider some how to obtain the effective hydrodynamics from this framework. So since I have to consider finite temperatures, I divide this metric tensor into time part and space part respectively. All are delta function. This is just 1 and 1. That's it. So here I set the energy momentum tensor interaction lambda equals set to be 0. So this is the RG flow for the time component metric tensor, RG flow, the space component metric tensor. And I just, the same thing before, and I just divide this into time component and space component. This is the bulk equation of motion, the same thing, time component and space component. The prescription is that I set the time component here and space component here. And as usual, I'm considering the vacuum solution, FG or phi.
I have a question.
Yes, please.
Go back to the previous slide.
Yes.
So the term involving the second derivative of the Green's function with respect to time, that makes it non-local in time as well?
Yes, but yes, right. I keep only all the local at present level. Yes, right. Basically, it should be non-local. Yes.
So it was before it was non-local, I thought, in some sense in space, but now it's non-local in space and time.
Yeah, right.
Interesting.
Previously, also non-local in space and time.
Oh, we did. I didn't notice that. Thanks.
Yeah. Here, yeah. So the vacuum solution, I assume translation invariance, or which minimize the free energy. So this is the mean field solution. So I consider some small perturbations, small fluctuations around this mean field solution. Accordingly, the green function, high energy green function of the high energy matter fluctuation is, I expand this linear order for fluctuations, time component metric, space component metric, order parameter, this component. Then this can be calculated from the green function equation, of course. This is the mean field solution. So now just plug it into the equational motion, and then I obtain for the mean field solution is given by, because this is translation invariant, I have omega is Majorana frequency, K is momentum integral. Now large T is given by small d plus 1. Beta is inverse temperature. So FG time component metric, space component metric, order parameter. So time component metric, evolution equation, space component metric, this is equation motion. This is certainly, so UV and IR boundary condition respectively. So what I want to say is this is a durable framework, although the result is quite non-linearly intertwined equation, but this is certainly durable in the mean field level. So what I'm expecting is, if suppose I did not solve this equation yet. Suppose I solve this equation, then I'm expecting maybe some horizon may appear from this one. This is just a speculation. So suppose I solve this equation as a function of c, then maybe I may find a black hole, ADS black hole, depending on this mass parameter. So I don't know. This is just speculation. Then in this background actually, for the linear fluctuation part, so the detailed expression is not important. So all these linear perturbations here, just keep then, so time component and space component. Also, this is equational motion for order parameter field. I expand up to the linear component. This is G derivative term, time derivative, space derivative, and UV and IR boundary condition, not important. So suppose I neglect this part, then if I compare the old paper of some famous old papers and so on, and here, so this is the metric tensor small fluctuation here. But this is this one. So suppose because here you have some ADS black hole, then the normal mode are given by diffusive mode. Here, this is our derived equation. If there is correspondence, this term and this term, each term by term, so it depends on the solution. If the mean field solution contains some horizon, then maybe I have some diffusive normal mode, then yeah, I don't know. Then I can have some effective hydrodynamic behavior from the first principle. This is just speculation. This is how it goes, the storyline. Already, so let me, although, yeah, for the time being, there is one part more, but at present, let me summarize the final part. There is some entanglement entry part, but for the time being, because time already passed, so let me summarize. So as you can see, the technical aspect is very simple. Just so it doesn't matter what kind of renormalization group transformation used, it doesn't matter. You can use real space, Polchinski algae, or Kadar block spin transformation, or you can use momentum space algae. Then new effective interactions are generated, and you keep such a term via update dual fields such as metric tensor and U1 gauge field, and also scalar field. Then such high energy quantum fluctuations described by Green function generate effective geometry through this recursive algebra transformation. Also now metric tensor and dual order parameter become fully dynamical. There we have their coupled equations motion. I showed the metric tensor evolution is nothing but algebra of coupling functions. Order parameter field evolution is nothing but algebra of order parameter, and IR boundary condition contains all the order quantum fractions are summed there. Also, I didn't derive yet, but I showed the prescription how I can obtain black hole solution and Hawking page transition and some effective hydrodynamics at high temperatures. Although due to lack of time, I skipped the entanglement entropy part. So yeah, so that's it. Thank you very much. Yeah.
Let's thank Ki-Seok for the interesting talk. Are there more questions?
For finally, one may ask the ON symmetry. So let me consider ON symmetry. To capture the ON symmetry, I introduce some background ON gauge field here and here. This is the external fictitious ON gauge field here and here. Then I repeat the same normalization. This is ON symmetry. Repeat the same normalization group transformation, although it is complicated, but essentially the same, except for this kinetic energy term. This kinetic energy term here, except for covariant derivative. This is the original kinetic term. This is the renormalization term. So second derivative is changed into some covariant derivative, some green function. So in order to update this one, you have some mixing between space component and flavor internal symmetric index. So in this respect, if you really deal with ON symmetry properly, the resulting theory is not so simple. This may give rise to some higher spin gauge theory. I don't know, I'm not sure, but yeah, this is just, yeah. So here, I did not take into account the ON symmetry properly. I just, yeah, considered just, yeah, mass interaction, self-interaction, that's it. So yeah, this is the, that I missed for the previous, yeah, comment. Yeah, that's it.
So I have a question.
Yes, please.
If I'm at finite temperature, take ZF, the IR cutoff, to the horizon position.
No, GF is IR. So horizon position should be less than GF, in my opinion. But here, but I'm not sure how the horizon appear. So diverge. So I don't know. I don't know. So there must be some cutoff here for this K integral. But how that related with GF? But how I can obtain cutoff? I don't know. How I can obtain some horizon less than GF? It's not clear. Yeah, I have to solve this equation. Yeah. Black hole solution. I don't know. Yeah.
So there are no more questions. So let's thank Ki-Seok again.
Thank you.
Yeah. Okay, so see you everybody next week. Thank you.
Yeah, thank you.